Welcome viewers to the second lecture of the online course Computer Numerical Control of Machine Tools and Processes. Today, we will be discussing about binary logic and logic gates. So, what are we really concerned about? We are concerned about, first of all, signals which are employed in case of control of CNC machines. They are in many cases they are binary valued signals. That means, they can take up two values, and in that case they undergo a number of combinations and they are used in decision making in CNC machines, and we will be having a quick look at these typical signals. From a power supply, we might be having a signal, and it can take up say a value of 0 volts, and which is sometimes referred to as low signal or 0 volts or value numerically 0, like that. A value of 5 volts may be referred to as high or 1 or 5 volts. It does not necessarily mean that it has to be a high voltage in order to be considered high. A low voltage also might be considered to be a high. It depends upon what convention we are following. So, in the same way, a signal might be varying between high voltage and low voltage, so that we can have a pulsed voltage as shown in the third picture, that A is taking up a value of 5 volts or 0 volts and changing over time. So, these are typically some digital signals that we are going to come across, and let us see what kind of operations can be done with them and what kind of mathematical or logical operations they follow. Now, just one moment. Yeah. So, generally when we are having these binary valued variables, for example, A and B, and as discussed before, they can take up two values. We are referring to those two values as 1 and 0. They might be 5 volts and 0 volts, they might be high level, low level, whatever. We are referring to them as 1 and 0. So, if there are certain relations between them which are defined by these logic operations. Mind you, in some cases they might be having mathematics like symbols, but they are not exactly mathematical operations. At least at this moment, we are only discussing logic operations. For example, how do these logic operations, what do they represent? For example, if I write A prime, it means just the opposite of A. Since A can have only two values, so if A is 1, A prime or A dash is 0. It is also sometimes referred to as complement of A. In the same way, if B is 1, then B prime or B dash is 0. If A is 0, then A prime is 1, like that. So, we have a list possible values of A, possible values of B, giving rise to 4 possible combinations, and for that we have A prime and B prime also written down. So, if A is 1 1 0 0, A prime must be 0 0 1 1, just the opposite. In the same way, there are some relational logic operations carried out between A and B. Say A plus B is written, it should be read as A or B. It is a logic operation which says that A or B is a function which will be having a value 1 if A and B both are 1, or if A is 1, B is 0, or if A is 0, B is 1, and in all the other cases it is 0. So, it is something like, let me give you an example. Suppose you and your friend, you are going for a particular say a particular celebration, or for going to a movie, etc., and the doorman asks for your tickets. Suppose both of you have your tickets, the doorman passes you. only one of you have a ticket, then also say he is very lenient, he passes. But if both of you do not have a ticket, then he does not pass you. This is A or B. So, A or B is represented as 1 1 1 0. What is A and B? A and B is not that lenient. Suppose the same doorman says both of you have to have tickets, otherwise I am not going to let you in. He represents A and B. Only when A is 1 and B is 1, A and B will be returning a value of 1. In all the other cases, no, 0. A XOR B gives another relation. It says if either A or B is 1, but not both, then the result is 1. So, even if both of them are 1, then also it does not return 1. It is called exclusive OR. And in the last column, we have written A hash B, just some arbitrary operation is defined as A hash B. If I ask you, can you tell me what kind of logic operation it represents? So, in that case you can do one thing, you can apply your common sense to find out, okay, does it look like any other logic operation? A or B? No. A and B? No. A XOR B? No. But if you complement A and B, that means A and B whole prime, then you will get A hash B. This is a way in which in many cases you will be able to build up circuits by comparing it with existing circuits. So, this way binary logic operations, they have a certain number of they obey certain laws, which we will have a quick look. For example, if you think of the complements, E or E dash is equal to 1. Why? Because at least one of them will be 1, and OR means that if one of them is 1, you will get a 1 as answer. E and E dash is 0, because at least one of them will be 0, and if you have a 0 ANDed with another variable, you will get a 0. So, in the same way, A or 1 is 1, A and 0 is 0, A and 1 is A, so on and so forth. The commutative law looks very much like addition, multiplication, etc. A or B is B or A. A and B is B and A. The distributive law is similar to mathematical relation. A and B or C is equal to A and B or A and C. Associative law is the place where you will find it does not look like the mathematical operations that we have. A or B and C is equal to A or B and A or C, and De Morgan's laws are very useful. For example, A or B whole prime is equal to A prime and B prime, etc. Now, we come for some symbols of logic gates. Logic gates can be realized through electronic circuitry, and this is how they are represented in by symbols. For example, two signals are coming in, they are binary signals, they can only take up two values, A and B, and the result is A and B, and a half moon shape represents the AND gate. In the same way, on the right hand side, the signal for the symbol for the OR gate is shown, A or B is the result. In the same way, the NOT gate, that means the complement, the NAND gate, the combination of AND gate and NOT gate, etc., these are shown. Of interest to us is the XOR gate, which is the exclusive OR. Now, let us do some exercises through which we will become conversant with the working of the logic gates. For example, say we set ourselves this particular task, that we have to find out a logic circuit which will be able to mathematically add 2 bits. That means that if I have 1 and 1, my circuit will be so designed that it can add up these two ones and give me a result of 2, which in binary is 1 0. It can add 1 and 0 and give a result of 1, and it can add 0 and 0 and give me a result of 0. So, this is mathematical addition, and with the help of logic circuits, logic operations, I have to represent these mathematical operations. So, I have written down the possible results of mathematical addition. Suppose A and B are being added. If you refer to the blue table, 1 plus 1 results in 1 0, which means basically 2. So, I have written down one column, the carry column and the sum column. So, 1 plus 1 is 1 0, 1 plus 0 is 0 1, 0 and 1 is 0 1, and 0 plus 0 is sum 0, carry 0. So, I have also written down the typical results that we have of A dash, B dash, A or B, A and B, etc., etc. So, if we have to represent sum and carry or build up circuits which will be giving us results of sum and carry, we can first compare quickly with the established or standard gates and find out whether they are already there. For example, sum is very much there, A and B. So, sum is represented by, whenever you are adding 2 bits, bit means binary digit. When you are adding up 2 bits, then sum is represented by A and B. And what is carry represented by? Carry is represented by A XOR B. So, if I build a particular circuit where I am simply employing A and B for obtaining sum and A XOR B for obtaining carry, my job is done. Let us have a look at that. That is it. I am having A and B coming in. I have divided them and sent one pair of A and B to the AND gate, and we are achieving carry as a result of this AND gate, and we are also having an XOR gate which is giving me the sum. So, this way I can add up 2 bits, whatever be their combination, the results are always going to be obtained as carry as the output of AND and sum as the output of XOR gate. It is called a half adder. However, if you look at say mathematical addition, I have shown here 2 bytes are being added. That means 8 digit binary number. If you add them, first 1 plus 1 will yield 1 0, the 0 comes down, takes the units place, and there is one carry over the next column. So, in the next column, if you see the color is different. Is it coming different? Yes. This blue colored column is therefore having an addition of mathematical addition of 3 bits. So, you might well have the addition of 3 bits whenever you are adding up 2 bytes together. So, let us have a quick look how this can be done. Mathematical addition of 3 bits. Whenever we are thinking of mathematical addition of 3 bits, what I have done is I have put them in columns of different possible combinations, and the results of sum and carry are written down, and those particular results which are yielding a 1, they are highlighted. For example, A, B and C can take up a combination of 1 1 1, which means that their addition will give us 3, which is represented by 1 1 in binary. So, carry will be 1 and sum will be 1. In the second row, we have A 1, B 1 and C 0. Their addition will yield a 2, which is 1 0 in binary. So, carry will be 1, sum will be 0. So, this way we have built up this particular table in which different combinations of A, B and C which are being added together, they are yielding different values of carry and sum. In that, what we have done is we have pinpointed those values which are having a value of 1 or high. So, that way if we look at say sum, I can say that the sum takes up a value of 1 in 4 cases, if A, B and C are all 1, or if A is 1 and B is 0 and C is 0, in that case sum is 1, or if A is 0 and B is 1 and C is 0, or if A is 0, B is 0 and C is 1. In none of the other cases the sum is 1, and these combinations can be expressed logically. In what way? We have written down sum is equal to, that means sum is 1 in cases where A and B and C, the first condition is written down, A and B and C, or is given as the mathematical or sign here, plus, sorry, not mathematical or sign, the logical or sign is given. So, we are basically writing sum is equal to A and B and C, or A and B dash and C dash, or A dash and B and C dash, or A dash and B dash and C. That means, all the cases where sum is 1, we have written down and connected them up with proper logical operations. In none of the other cases, we are going to have a 1 for sum, and for these cases we have connected them connected the variables up in such a way that those unit building blocks, they are going to yield a 1. So, suppose A is 1, B is 1, C is 1. The first term of sum is going to yield a 1 and the others are going to yield zeros. So, sum is going to be 1 in that case. So, this circuit will represent a value, the value of sum in any of these 8 cases. Let us say we take A is 0, B is 0, C is 0. All these terms will be zeros. So, sum will be equal to 0. So, it is built in such a way, by taking individually the cases where it is equal to 1, we build up a circuit which is going to yield a 1 only in these 4 cases. In the other cases, it is going to yield a 0, and that way we have built up the logical representation of the mathematical operation of sum. In the same way, if you take carry, carry is 1 in the highlighted cases, and correspondingly we have built up the logical representation of these particular cases and connected them up with logical or operation, in this case or this case or this case, like that. Now, is it, what are we ultimately getting? We are getting sum to be represented by a particular logic circuit or a combination of logic gates. How do we utilize it? We can simplify it. Let us have a look. For example, carry. Carry is A and B and C, or A and B and C dash, or A dash and B and C, or A and B dash and C. What we are doing here is that, since in logic Boolean algebra, A plus A is equal to A, I can add any number of A's to itself to get the same value. So, in the same way, I can add any number of A and B and C to this one without any change in the ultimate result. So, what we have done is, we have added 2 more A and B and C to these terms. So, what do we have? The first term is A and B and C plus A and B and C dash, then again we add A and B and C. So, this way the first 2 terms will allow us to take A and B common with C plus C dash. The third and the fourth term will allow us to take B and C common, A plus A dash. So, this way C plus C dash is equal to A plus A dash is equal to B plus B dash equal to 1. Therefore, this comes out to be A and B or B and C or E and C. So, carry is simplified this way. In the same way, after writing out the expression of sum, we simplify it by taking A common from the first two terms, getting B and C plus B dash and C dash in brackets, or A dash common from the last two terms with B and C dash plus B dash and C in brackets. Now, B and C dash plus B dash and or B dash and C is nothing but B XOR C. So, the last bracketed term becomes B XOR C, and the first bracketed term B and C or B dash and C dash can be shown to be nothing but the complement of B XOR C. In what way? We have taken its complement, applied De Morgan's law, and ultimately obtained B XOR C whole prime, and therefore, we are saying this particular term simplifies to A and B XOR C dash plus A and B XOR C dash or A prime and B XOR C equal to A XOR B XOR C. So, this is the simplified form of the sum. Let us take a small numerical problem. There is a grinding machine in which coolant is to be applied automatically if the temperature is greater or equal to 60 degrees centigrade, the surface speed is greater than 20 meters per second, and the table feed is less or equal to 15 meters per minute. And suppose we are having sensors which are taking some signals, which are developing signals where A is equal to 0 when temperature is less than 60 degrees and equal to 1 otherwise, B is equal to 0 when the surface speed is less than 20 meters per second and 1 otherwise, and C is 0 when the feed is less than 15 meters per minute and 1 less or equal to 15 meters per minute and 1 when in other cases. The question is, make a circuit which would send an output signal of S equal to 1 when coolant is supposed to be applied, otherwise 0. So, look at the picture. The grinding machine has 3 outputs and there is a black box to be designed by you which sends out S, which should be 1 when coolant is to be applied and a 0 when coolant is not to be applied. So, let us see what this circuit should be like. First of all, we have pinpointed the 3 cases where the signal is supposed to be 1. The output signal should be 1 in these 3 cases, and therefore, we are arguing this way that signal should be 1, following the argument of the previous example. Signal should be 1 if A and B and C is 1, or A and B dash and C is 1, or if A and B and C dash is 1. So, having understood that, what we are doing? We are taking ABC and adding ABC, one more ABC at the end. So, from the first 2 terms, we are getting AC common, A and C is taken common and it is ANDed with B or B dash, plus AB is taken common and it is ANDed with C or C dash. So, they are B plus B dash, B or B dash is equal to C or C dash equal to 1. So, that we are ultimately having A and C or A and B, which is equal to A and B or C. So, we have this simple circuit, okay, A ANDed with B or C. This simple circuit will be controlling successfully the flow of coolant to a grinding machine. These 3 inputs, just to remind you, they are concerned with temperature, surface speed and feed of a grinding machine. Thank you.